This video will be a force vector directed along a line example problem. The way to distinguish this type of problem from other vector addition problems you've done before is that you don't have any angles. The problem asks for a resultant force, but you don't have any angles to do cosine, sine, or similar triangles with. Instead, you have XYZ coordinates of endpoints of a line. This type of problem presents itself in the real world usually in the form of cables, because it's very difficult to measure the angle of a cable in the real world, but it's very easy to measure the distance to the two endpoints of the cable. So instead of using trigonometry, you're going to use unit vectors. So this problem will start off using position vectors and unit vectors to convert each of these two forces into Cartesian form, and then you'll do the vector addition in Cartesian form just like normal. I'm Dr. Bernard, your engineering professor. If you're new to my channel, welcome. Most students will say that the junior year engineering courses are the hardest, but I've actually found in 7 years of teaching that it's actually the sophomore year where most students end up changing majors if they don't do very well. The purpose of this channel is to get you confidently through your sophomore year and develop a strong enough skill set to carry you through the harder work that's to come as a junior, and then ultimately to pass the FE exam on your first try during your senior year. Getting into this example problem, I'm going to start off by setting up my page. So in my class, I like to use a given, find, concept, solution format. Your professor may have something a little bit different, but should probably generally resemble something close to this. And what I put here in the concept, along with some of the key words of different parts of the solution, are going to be the main equation that's going to be used to find the final answer. So in this case, in order to find the resultant force, we're going to need vectors in Cartesian form, and that means we're going to need these force vectors. So if we can find F and U on the right-hand side, then we can get to that point to find the final answer. You may be too young, but you remember that old Make 7 Up Yours commercial?
And I just came up with a great new slogan. Make 7 up yours. Make 7 up yours. Make 7 up yours. Same to you. Same to me.
You probably want to make sure your professor has a sense of humor before you go using that joke yourself. Leave a comment if you actually remember that 7-Up commercial. Make me feel a little bit less old. And F, right, those values are already known. That's a 350 newtons and 400 newtons that we already have. So really, we're just looking for unit vectors. If we can find the unit vectors, we can solve this problem. So this here in blue is going to be the main version of the equation that we're going to be using. Since we know we already have F, we just need the position vector and the magnitude of the position, and then we'll be able to find our force. Step 1, identify the XYZ coordinates for each relevant point. And you find each of these just by looking at the picture. You're mainly being mindful of whether terms are positive or negative, and making sure you don't get the X and Y axis mixed up. Your next step is going to be the position vector for each line. And these position vectors are found by subtracting the end of the line minus the beginning. So since each of the forces go from A to B and then A to C, the position vectors are going to be RB minus RA and then RC minus RA. So the vector for RAB, minus 3I, minus 4J, minus 10K. You may also be able to skip step 1 and just jump directly to step 2. If you're able to look at the picture and just go from A to B, you may be able to just read this RAB vector directly off the picture and skip that first step. So now repeating for the vector from A to C. And I went ahead and underlined the two intermediate steps there that are going to be the terms that we use going forward. So if you're ever not sure where to go next, it's always good to look back at your equation. So if we're using the force vector over the magnitude of the force equals a position vector over the magnitude of the position, you can see now that we have those two terms, and that was the one that we are looking for. So this term must come next. The magnitude of the position, which is going to be, in this case, the length of the cable. So the length of the cable is essentially going to be a three-dimensional Pythagorean theorem using each of these position vectors. If a student were to make a mistake on this step, it would probably come as a result of the negative signs. Each of these negative numbers needs to be squared underneath the radical. So all of the terms should be added to each other. The first term should be 9 plus 16 plus 100, not negative 9 or negative 16. So you may want to actually just ignore those negative signs and just use all positive signs underneath the square root. You'll still get to the same answer because negative 3 squared and 3 squared both equal 9. So now we're ready to move on to step 4, which is finding the force vectors in Cartesian form. Here I've rearranged the equation slightly to get the force vector alone on the left-hand side by itself. Since F1 corresponds to FAB, I'm using the force vector for force 1 and the two position vectors for RAB. So with a little calculator work, we get this answer of negative 93I minus 125J minus 313K, and put brackets around the whole thing to show that all those terms have newtons as their units. At this point, because there's a lot of decimals and fractions involved, it's a good chance to double check and just make sure that this answer makes sense and that you didn't make any calculator errors. And the way you can actually check this is to see if this vector has magnitude of 350. And so we can set up a big square root of 93.91 squared plus 125.23 squared plus 313.04 squared. And put that in your calculator and do a square root and see this comes out to be 349.99, which is just a rounding error away from 350. So if you got a different answer and not 350 right there, that would tell you that you actually made a calculator error here on this last step. We can repeat this then for force 2, and that leads to a final answer of 176.1 I plus 70.44 J minus 352.18 K. And to do a quick double check, and that came out to 400.00. So again, we can be confident now that there were no math errors made in this last step. So step 5, vector addition in Cartesian form. And for this step, we'll just add F1 and F2 together, each of the I terms, then the J terms, then the K terms, each separately. So with a little calculator work, that comes out to 82.19 I minus 54.79 J minus 665.22 K, and newtons for the units for the whole thing. So first I'll box this as a final answer, but I do want to go back to the initial picture and see if this answer actually does make sense. Usually in statics, it's a very visual course. You can usually look at least plus sign and minus signs or just general relative magnitudes, get an idea and make sure that your answer is feasible. So looking in the x direction first, we see that F2 is actually pulling much more in the x direction, right? It's pulling both with a stronger force of 400 newtons, and it's going all the way to point C, which is at x equals 5, which is a little bit further away than B's at x equal -3. So it does make sense that our I direction would be a positive value because F2 is going to be dominant in that direction. Looking at the y direction, we can see that F1 is a little bit weaker, but in the y direction, point B is at -4, whereas point C is only at +2. So it does make sense in this case that we could get a negative answer in the y direction, again, because F1 is pulling more negative in the y direction than F2 is pulling positive. And then in the z direction, the 665 is negative. It makes sense that this number is much larger than both of the other two because both forces are pulling down as opposed to in the x and y direction where the two forces were pulling against each other. Depending on how your problem is framed, this might be a final answer. In this case, I just asked for the resultant force, so you can feel free to leave your answer in Cartesian form. Instead, if you had been asked to find a magnitude and coordinate direction angles, you might have to go an extra step or two further and find the magnitude of this resultant vector, or do some inverse cosines in order to find the angles. If you found this video helpful, consider subscribing to my channel so you can see more example problems like this. I also post thermodynamics, fluid mechanics this semester, as well as general college tips to make you a better student overall. Thanks again and enjoy the rest of your day.